So just a couple of lines. I'm sure many of you know Pravata quite well. He's the Department of High Energy Physics colleague for all of us. Just to say a couple of words about him, he actually completed his MSc and in physics from Utkal University in Bhubaneswar. And of course, he is our own product as far as PhD is concerned. He did his PhD from TIFR Mumbai, and he has been associated with the CREPS 3 experiment, about which he is going to speak for almost a couple of decades, and essentially worked in all major R&D activities which are undertaken for this experiment, including the development of plastic scintillator detectors and data analysis framework for fast and efficient analysis of CREPS 3 data. Some of it, what work he has done earlier actually become part of his thesis, and particularly his work on scintillation detectors, fibers, the signal transmission through scintillator fiber has been, in fact, such a great reference for many students who joined later. And I must say that that work has been quite seminal in the detector area, R&D area. He leads the physics analysis efforts of CREPS 3. He is currently, of course, the PI of CREPS 3 experiment. Some of the recognitions that came in his way are the IUPAP representative to the Scientific Committee on Solar Terrestrial Physics Bureau. SCOSTEP is an international body to promote solar terrestrial physics, and its permanent observer of the United Nations Committee on Peaceful Uses of Outer Space. He is also a member of India's Mega Science Vision, about which I'm sure you heard about it, Mega Science Vision 2035. And he served 3 times on the Scientific Program Committee of the International Cosmic Ray Conference, which is a flagship conference on cosmic ray physics called ICRC, which is in the field of astroparticle physics and cosmic rays and related fields. So with these words, let me invite Pravata for today's colloquium.
Yeah. Thank you, Dr. Satyanarayan, for the kind introduction. Also, thank you for arranging this talk. Good evening and welcome. Thank you all the participants who are listening to this talk, either being present here physically or through Zoom or YouTube. My name is Mohanty. I am going to talk on the topic impacts of solar storm. I will start with an introduction to various solar phenomena. Then I will talk about what is a solar storm, how they impact the Earth. Then I will talk about the recent incident on 4th February this month, when the SpaceX company lost 40 new satellites due to a solar storm. On the next day they were launched. Then finally I will discuss about the potentials of the CREPS 3 experiment in which I am involved to study and predict solar storms. As we know, there will not have any life without the sun. So the sun directly controls the life on Earth. Okay. So despite the lot of research, we have not been very successful in predicting the behavior of the sun. I don't know, it is not moving. What should I do? To go backward. This is something coming on the way. You can push it little down. You can push it little down. No. Yeah. Okay. Thank you. Good. So the sun's activity varies with a 11-year cycle, and it is measured in terms of variation in the number of sunspot that appears on the sun surface. The magnetic field of the sun flips during each solar cycle. You can see the left image. So how sunspot varies during 23rd solar cycle. 23rd solar cycle started in 1996, and you have maximum number of sunspot during 2001. You can see the right side graph. This is sunspot, a function of year. You can see the 24th solar cycle is stronger than the 23rd solar cycle. The 25th solar cycle started in December 2009. The activity is increasing. Although it is predicted the 25th solar cycle will be similar to 24th, but we don't know. We have to wait and watch. What is? I think I have to. Yeah. I think it's Okay, here is an interesting paper which shows the coincidence of world's great viral pandemics with the sunspot extrema. What I am showing here, a time period of 270 years, starting from sunspot cycle 1, which started around 1755. As you can see here, there are pandemics like dengue fever, smallpox, cholera, malaria, including Spanish flu, then AIDS, smallpox, yellow fever, SARS, swine flu, MERS, Ebola, and even COVID-19 pandemic has a correlation with the sunspot extrema, sunspot maximum or minimum. Although this paper shows a correlation study, but however it does not say much about how the sunspot extrema could cause the emergence of a new virus. As we know, sun rotates with around its own axis. The sun rotates faster at the equator compared to the poles. The rotation period of the sun at the equator is 24.5 days and 38 days at the poles. Since it is not a solid body, it has a differential rotation. That's why the rotation speed is different at the equator than the poles. Sun's magnetic field are aligned north to south. Because of differential rotation, then the magnetic field get twisted. So something disappear. Okay. So because of this, the magnetic field energy gets built up, and then it bursts where the sunspot appear. Sunspots are the temporary phenomena on sun's photosphere that appears as spots darker than the surrounding areas. They are the regions of reduced surface temperature caused by the concentration of magnetic flux that inhibit convective transport of heat from the interior of the sun to the surface. As you can see here in the left side image, the sunspots, although they appear to be small, but the actual size of the sunspots could be several thousand kilometers, even more than 100,000 kilometers. And the sunspots appear as pairs due to the opposite magnetic polarity. The built-up magnetic energy are released from the sun through solar flares on a time scale of minutes. The electromagnetic radiation, which are emitted in all wavelengths, ranging from radio to optical to X-ray and gamma rays. The amount of energy released is equivalent to millions of 100 megaton hydrogen bombs exploding at the same time. Here is a video. You can see a solar flare on the right side, and this is a coronal mass ejection. The electromagnetic radiation from the sun, it takes about 8 minutes to reach the earth. The increased level of X-rays and extreme ultraviolet radiation result in ionization in the lower layer of the ionosphere on the sun side of the earth. The high frequency radio signal, which is supposed to be reflected by the ionosphere, either degraded or completely absorbed, causing radio blackout. On 3rd July last year, there is a solar flare which caused radio blackout in several continents, including America, Africa, and Europe. You can see in the red color here. There is another phenomena called coronal mass ejection. They are the main driver of solar storms and space weather. A coronal mass ejection expels vast cloud of magnetic flux as plasma into the interplanetary space. The CMEs are associated with the flare, but not always. They take about 1 to 3 days to reach the earth depending on speed, and the CMEs occur about 3.5 per day near solar maximum and about 0.2 near solar minimum. The average ejected mass is 1 trillion kg. On the right hand side, you can see a coronagraph image of a CME ejected out from the sun surface. It's a huge CME and it's anchored to the sun surface. If the CME carries a strong south-oriented magnetic field opposite to that of Earth, the two magnetic fields of opposite polarity, they can interact each other, causing weakening of Earth magnetic field, which will allow solar wind plasma to flow into the magnetosphere. This can trigger geomagnetic storms. So geomagnetic storms are categorized G1 to G5 class based on the global average change of the horizontal magnetic field that is measured by some magnetic equatorial stations. Due to the geomagnetic storm, the current in the ionosphere as well as the energetic particles that precipitate into the ionosphere and the energy in form of heat that can increase the density in the upper layer, which is called thermosphere. And this can cause dragging of the satellites, which I will be talking after a couple of slides. Because they are itself particles. The CME is a plasma which contains protons and electrons. Yes, yes, yeah.
There is a question. Can you please also repeat the question and then answer?
Yes, sure. Here is a video how a CME released from the sun surface, they interact in the magnetosphere. You can watch it. So once CME come to the magnetosphere, they can compress the magnetosphere and they also can reconnect with the earth magnetic field. As you can see at the night side, there will be a reconnection point, and after that you can see the flow of the plasma and you can see the aurora which are created by force. Auroras or polar lights, they are caused by a result of the precipitation of electrons and protons into the upper atmosphere during geomagnetic storm, which create ionization and excitation of atmospheric constituents that emit light of varying color and complexity. As you can see a image of a beautiful aurora here. The impact from the geomagnetic storms are wide ranging with potentially significant consequences. They can impact GPS, satellite operations, manned space flight, aircraft operation, including power grid operations. Here I am giving a few examples the impact of geomagnetic storms in the recent times. There is a geomagnetic storm which occurred in March 1989. So that geomagnetic storm caused failure of a transformer, in a transmission line in Quebec, and because of that, the entire transmission line of the power grid collapsed. So it caused 6 million people without power for 9 hours, and also cost more than $2 billion. And another incident happened in January 1994 due to another space weather event, when there are two Canadian satellites called Anik 1, E1, Anik Muon, they are affected. So after the failure of Anik E1, then there are something like 50 Canadian communities, they did not have telephone service, and the Canadian press that could not provide news to more than 100 newspapers and 450 radio stations. After the failure of Anik 1, Anik E1 failed after few hours. However, the Anik E1 could be restored in a couple of hours, but it took about more than 7 months to restore Anik E2. So that cost more than $50 to $60 million. And more recent times, that is in October, November 2003, these are the strongest geomagnetic storm events in recent times that cause GPS outage, radio blackouts, and so on. And in January 2005, due to a geomagnetic storm, about 26 United States airlines had to be diverted. There was a event called Carrington Event. This is the most strongest geomagnetic storm event in the recorded history. It caused strong auroral displays that were reported globally, called sparking and fire in multiple telegraph system. Even that time, it is primarily the telegraph, the primary technology, the telegraph system, and the telegraph operator could get electrical shocks on their fingers. Auroras are visible even from low latitude regions. The Coronal Observatory, which is close to TIFR near RC Church, so that time it was measuring the magnetic field, and the data from the Coronal Observatory is the most important among all other observatories in the world. It measured a change of 1600 nanotesla in Earth magnetic field, which you can see on the right side figure. So even now, people are studying this event, producing papers in high-profile journals. There could be several 100,000 papers on this Carrington event. So geomagnetic storm on the scale of Carrington, if it happens today, it could cause trillions of dollars of damage to satellites, power grids, radio communication, could even cause electrical blackouts on a massive scale. So that could not be recorded for weeks, months, even years. Unfortunately, Earth missed a similar kind of event in July 2012 by approximately 9 days, because it was pointed to in another directions. Now let me discuss about the recent incident. The Space Exploration Technology Corporation, which is doing a business at SpaceX, it was founded in 2002 by Elon Musk with the goal of reducing space transportation cost to enable colonization of Mars. It manufactures Falcon 9, Falcon Heavy launch vehicles, several rocket engines, cargo dragons, Crew spacecraft, and Starlink communication satellites. Starlink is a satellite constellation with the aim to provide high-speed satellite internet to most of the Earth. They have already launched more than 1,700 satellites till today, and the objective is to launch 42,000 satellites. Astronomers have raised a concern that it can affect the ground astronomy. And here, this SpaceX also launched a dummy payload that is, I think, Tesla car. On February 3rd, this month, the SpaceX launched 49 Starlink satellites from the Launch Complex 39A at Kennedy Space Center in Florida to a parking orbit with a perigee of 200 km above Earth. The idea of deploying to the parking orbit is that in case a satellite does not pass initial system checkouts, it will be quickly deorbited by atmospheric drag, because these are low Earth orbit. There still there will be atmosphere. Unfortunately, the satellites were impacted by a geomagnetic storm which occurred on 4th February. The atmosphere, this is a minor class geomagnetic storm. As we know, the storm caused the atmosphere to warm, atmospheric density at low deployment altitudes to increase. In fact, the onboard GPS suggests that the escalation speed and severity of the storm caused atmospheric drag to increase up to 50% higher than during the previous launches. Starlink team commanded the satellites into a safe mode where they could fly edge on like a paper of sheet, minimize the drag to effectively take over the storm. But preliminary analysis showed the increased drag at the low altitudes prevented the satellites from leaving safe mode to orbit maneuver or raising the orbit. So now most of these 40 satellites would have re-entered to the atmosphere, or they will be re-entering. Of course, these are small satellites. They will burn while entering to the Earth. Okay, I think I have enough time. Yeah. Yes. So let me change to another topic. How cosmic rays could play an important role in probing solar storm and space weather. As we know, cosmic rays are the most energetic particles present in the nature. Their energy ranges from 10 to the power 8 to 10 to the power 20 electron volt. The highest cosmic rays energy is million times that what you can achieve by the man-made accelerator today. They are the nuclei of hydrogen and helium constituting 99%, heavier elements up to iron, which is about 1%. The cosmic rays are originated outside our solar system. They entered to the solar system and they are affected by the interplanetary magnetic field and solar wind. Particularly the low energy cosmic rays are affected below 100 GeV. So they can be used as an excellent probe for short and long term solar phenomena and space weather. Here an example how cosmic rays are modulated by solar effects. On the top tunnel, this is the cosmic ray flux measured by a neutron monitor over a period of 6 solar cycle, and at the bottom it is the sunspot number during the same period. You can see there is an anti-correlation between them. Basically, when the solar activity is maximum, you have a less cosmic ray intensity and vice versa. Cosmic rays, when they enter into the atmosphere, they produce a shower of particles, as you can see on the right side, including muons, electrons, photons, and the hadrons. Earth magnetic field cannot shield high energy cosmic rays above certain threshold. It's called geomagnetic cutoff rigidity, which is about 20 GeV near the magnetic equator. During a geomagnetic storm, more low energy cosmic rays they can enter into the magnetosphere because of lowering of the cutoff rigidity, and excess of these cosmic rays they can endanger life of astronauts. The GRACE-3 experiment at Ooty, which is located at an altitude of 2,200 meters, it is designed to study cosmic rays and their properties. It consists of two major detector components, 400 plastic scintillators. Each of them is a 1 meter square area separated by 8 meter, spread over an area of 2,500 square meter. The each white conical structure what you see in the picture, they are the scintillator detectors. The second major component is 560 meter square Muon telescope that consists of 3712 proportional counters. Each is 6 meter long and 10 centimeter by 10 centimeter cross sections. And we are in the process of expanding the Muon telescope to have another Muon telescope similar area. GRACE 3 is a growing collaborations. At present, we have 19 institutions, 13 from India and 6 from Japan. And the Indian institutions as marked by yellow, marked by green markers in the Indian map. They are spread over all over the country. We have several ongoing PhD students from TIFR as well as these collaborative institutions. So this is a view of the GRACE 3 Muon telescope. There are 4 stations. Each station consists of 4 modules. Okay, and this is a view of one of the Muon telescope. There are 2 modules which are in the front and 2 modules on the back side, and each module consists of 4 layers of proportional counters. Here, let's say layer 1 and layer 3, the proportional counters are aligned in north-south directions, and layer 2 and layer 3 they are aligned in east-west directions, and then you have concrete in between and concrete on the top. So the concrete, they act as an observer or filter to electromagnetic components and hadrons. So it allows muons which are the penetrating components. So basically it detects muons above 1 GeV threshold. Here is a Jan4 simulation of the Muon telescope. Here I have taken 3 particles, 1, 2, 3. One is a muon, as you can see, it passed through the concrete as well as it passed through 4 layers of proportional counters, whereas 2 and 3 hadron electron, they produced a shower and stopped in the concrete itself. So the idea having a Muon telescope that you filter out all other components to detect the muons. So by this process, by tracking this, you could find the direction of each muon, and this tracking provides 169 direction measurement of muons with an average angular resolution of 4 degrees. Per day, we record 3 million muons. Per day we record 4 billion muons, and per minute 3 million muons with a statistical accuracy of 0.1% per minute. So this is because of this. This is the most this is the most efficient Muon telescope in the world. There is a muon burst which occurred on 22nd June 2005, Ooty midnight. All the 16 modules of the Muon telescope recorded the burst at the same time, lasting for 2 hours. You could see here. So this was presented in a weekly meeting of the GRACE 3 collaborations, where it struck me this unusual variations. That is where the work started, which I am going to discuss in these few slides. So there is a strong coronal mass ejection on 22nd June 2015, which triggered a severe class geomagnetic storm, G4 class. The coronal mass ejection was identified by measurements of satellites which are located at first Lagrangian point called L1 point, which are located 1.5 million kilometers from the Earth. So the speed measured by L1 satellite suddenly increased from 400 kilometers to 700 kilometers, and at the same time the interplanetary magnetic field also increased, as you can see here. However, interestingly, the BZ component of the magnetic field, which is aligned along the north-south directions, that is the opposite to the magnetic field of the Earth, that turned negative, means it was strongly south oriented. And interestingly, you can see the muon flux, which was measured by GRACE 3 Muon telescope. There is a surge of the muons, and since these two profiles look very similar, we inverted the polarity of the BZ magnetic field, which is shown in the right side, and it gave a very strong correlations. So which made us to believe the magnetic field must have some role for causing this burst of muons. Of course, we started the hypothesis due to the geomagnetic storm. There must be some weakening of Earth magnetic field that would have reduced the cutoff rigidity or the cutoff of the Earth magnetic field. This would have allowed more low energy cosmic ray to enter into the Earth atmosphere, producing muons. But however, to prove this hypothesis, we had to carry out extensive simulations using a 1280 computer cluster at Ooty. It took almost more than several months. So here, what I am showing here, the muon burst, the measurements are shown in the blue color in night direction of the muon telescope, and the simulations which are shown in the red color, and there is a fairly good agreement between them. So what made us to conclude here, there is a cutoff rigidity change of 0.5 to 0.7 GeV, and there is a weakening of Earth magnetic field about 700 non-Tesla. More interestingly, the simulation showed the cosmic ray muons, or the cosmic rays, actually they entered from the day side, and they bend more than 210 degrees to be detected at the night side by the aggressive muon telescope. So this result was published in PRL with the title "Transient Weakening of Earth Magnetic Field Proved by a Cosmic Ray Burst." Here I am just reading a few lines of the abstract. The simultaneous occurrence of the burst in all 9 directions suggests that the origin close to the Earth. It also indicates a transient weakening of Earth magnetic field. Is it possible to move? And may hold better clues for understanding of future superstorm that could cripple the modern technology infrastructure on Earth, endanger the lives of the astronauts in space. Okay, that's okay. That's okay. Yeah. Following the publication, it received a worldwide attention, worldwide coverage. The results were reported more than 1,000 reports, more than 100 countries in 37 languages. The reports, if you are interested, here it is there in the website. It was reported by BBC News, Science, and many other scientific journals and so on. What is more interesting, we found that is important for space weather prediction and warning. There is a delay in the arrival of this storm. So this the storm or the CME, it takes about 36 minutes from the L1 point to the Earth at a speed of 700 kilometers seconds. Okay, so the predicted so it is predicted, the arrival time on the Earth is predicted based on the speed at L1 point, but what we found, our burst occurs with a 28 minutes delay. Okay, so this is important. So why there is a 28 minutes delay? We do not know, because once the CME leaves the L1 point and enters the magnetosphere, it has no knowledge how it is going to evolve. However, we speculate when it enters the magnetosphere, it would have been slowed down by the pressure of the magnetosphere. But of course, there are a lot of work need to be done in this front. But let me tell you how it is important in terms of space weather warning and economy. That is not understood. Yeah. So origin of the 28 minutes delay is not understood. Yes. So the GRACE 3, the satellite data will say, for example, the storm will arrive on the Earth in 36 minutes. But however, the GRACE 3 observation will tell you it will take another additional 28-minute delay. Okay. So this is important because premature shutdown of the electrical systems or technology, that will have a huge economic cost.
It is always 28 minutes because depends upon the magnitude. We are continuously almost 1,000 kilometers above the Earth. It's a rotating kind of phenomenon. So it's all depends on all that time. It's most complex and dynamic system. So it's not quite sure that 28 minutes or that is just my.
Okay.
Just following on that, if you have another such event, and there also it's like one set of event you find out there. But then if you have replication of the sampling and the 28 forms,
yes,
that would be really like a
yeah. So your question, if you have a similar such events with the delay, okay. So now I would pose a question: why sun will give you one event? Okay. So let me go to the next slide. We'll look to the GRACE 3 data, which is recorded for last 20 years, and this is a work of Miran Juveri. So what he found, 70 burst-like events in this 23 years of data. You can here I am showing some of them. As you can see here, the blue one, that is the actual Muon event, where the red one is the simulated event based on the magnetic field which are observed at L1 point. As you can see, each of them, there is a delay between the Muon burst as well as what you expect based on the satellite data. So the delay what you are asking, here is the answer. It is not just some single value. You can see it is different for different events, but we are seeing here it varies in the 6 events 20 minutes to more than 1 hour. Yeah. So it will be interesting to understand why this delay is occurring. Okay, right now we are doing it in next day, but it can be done in a few minutes. Yeah. Okay, I am coming to the next slide. So what is the outlook? Advance warning of storm arrival is necessary to save the technology driven Earth. So far, satellite measurements of IMF at L1 cannot accurately predict the scale or severity of the storm and their arrival time. So there is a lot of uncertainty. Our June 22nd event took 2 months of computing time using 1280 core computing cluster. However, a new algorithm has been developed which can simulate the burst profile in a fraction of a second. Okay. So, however, the real-time IMF data from satellite is necessary to simulate the event. Data should be also analyzed promptly in an automated manner, which needs some work. We need to develop algorithms of storm arrival and test using the already known events. So, what I want to say here, you need both space and ground based measurements for the prediction of space weather. Here, many of you know that we have a mission called Aditya L1. I cannot comment much about the status, but however, this Aditya L1, it has several instruments which can measure many things, including imaging of the sun as a coronagraph and measuring the magnetic field data, solar wind. Yeah. So, since by the name, it will be launched at L1 orbit. And this is GRACE 3 is a ground based measurement. So both ground based and this is space based mission is very important, where this can provide the data immediately, and the ground based data like GRACE 3 that can provide much more information regarding the delay. In fact, I would like to share that the 22nd June 2015 event, it took several months to analyze the data. It is not because of that, it is because we had to wait several months to get the data available from NASA. So there is a symposium which is happening next week from Monday, 21st, 25th February. So this is called SCOSTEP 15th Quadronnial Solar Terrestrial Physics Symposium, ST15. This is hosted by Indian Institute of Geomagnetism. Of course, there are several topics, including Sun-Earth connection, then Sun planetary space, geospace, space weather, Earth atmosphere, and there is a session called Space Weather Prediction and Implementation. I have been a convener of this session. Yeah, thank you.
Okay, thanks, Pravata, for very nice, crisp, but also taking through all the aspects of this particular natural phenomena, but also giving good idea about the capability of the GRACE instrument for doing the space weather. Also, of course, coming to the end, where you also said that it's in some sense it has to be a combined effort of both space instrumentation and ground instrumentation. Okay. Let us take some questions here.
Yeah. So I have 3 questions. One is when you solar cycle, right? You said first solar cycle or something that happened in 1800 something or 1900. This is your fourth.
Yeah.
You showed that slide number 4, 5 or something. If you go back, I just wanted to hear that. Is that because before that we didn't have technology to some? Yeah, so that's 1750, for example, right? Sun is there since so you said the past one is 1750 just because we didn't have anything before that. The data was not available. Is that right? Or
before that, people are counting.
Began from there.
Yes, before that, people are counting the sunspots. Even the Newton, Isaac Newton, he also involved in counting this sunspots, but they are not a proper record that time.
Okay. Yeah. So that is first thing, and then second thing, that 26-minute or whatever delay you said. Is there anything with your experiment, any particular angle you can bring in to try to identify the source of this delay? Is there anything you can think of with the GRACE 3 data, or that is, or even like bringing some complementary measurement from somewhere else, trying to pin down what could be the cause of this delay?
Yeah, it's a good question. In terms of data, we are very sure there is a delay. There is no doubt on that. But why this delay? Of course, currently we have not much idea on this one. So it need to understand in terms of various solar parameters. Yeah. it involves some modeling. Yes.
Yeah, it's a very nice talk. I mean, this kind of things always very fascinating. One thing which Gagan was asking, since you are senior detection, the satellite might have given a straight line arrival of the stroke. But in your observation, you say that it has begin at the day and reached at the night by bending. So I would taken that distance which it takes to reach on your side. And you showed a nice bending of the cosmic. That's I think I feel the reason, maybe something else. What about the satellite position itself? Because today you have a satellite position at one point and your telescope you are at one point, and it's all changing. I mean, so with that reference, how you will be having accurate about this. It's good that if you can predict it's even 10 minutes in, addition to the what predicted by the satellite, which give a good room for us to act in future. But it's a good thing.
Okay. Yeah. See, coming to your first question, let me answer. So the bending of the cosmic rays from day side to the night side, it does not take time because these are relativistic charged particle of very high energy of 20 GeV, for example. So it will be simultaneous. So there will be no delay or insignificant delay by getting the cosmic rays which entered at the day side and coming to the night side. And coming to your second questions, yes, the satellite positions. See, the data from the satellite, it transmitted to the ground in 5 seconds by radio. Okay, so that is no problem. Only the arrival of storm CME to the Earth after it left the satellite, that takes long time because the speed of about 500 to 700 kilometers or so, several hundred kilometers.
There's one question from the Zoom. Okay, the question is, just give me a second. This is from Devesh. The question is, are you people using ML/AI in the new algorithm regarding prediction of the storms? I think you talked about something new algorithm.
No. So far, we have not got into any algorithm. So I also have not much idea about this algorithm.
Just a minute. There is another question from Sunil. Yeah.
Okay, Prabhat, anyway, excellent talk. I wanted to make a comment, and that is, while it's true that observations required are both, from satellite as well as from ground, and I just would like to add that during the ICRC held last July, there was a discussion with the people who are responsible for monitoring space weather using solar orbiter. And we are already, that very well. I was just sharing this information that they are very excited about this possibility that we can combine ground-based observations with spaceborne observations. Because at the end of the day, what matters is, what the space weather does to Earth. It is nice to know what's happening in space, but ultimately everybody's objective is what happens at Earth. And that is where an instrument like Graves 3 becomes extremely important because it gives us information of its impact on Earth. So I think in coming weeks and months, as one pushes the analysis along, I think we'll have a much better understanding, or at least some of the aspects of space weather. It is a vast area, but I think that's where the Muon telescope will play a very important role.
Yeah, thank you for the comment.
Okay, just a couple of questions, but very related from YouTube. This is Abhinav Chaudhary. The question is, can neutrinos be used to predict solar storms? something very similar is, can neutrinos from solar flares reveal something new about the property of solar from the neutrinos?
Okay, I am not the expert in this, but what I can say, neutrino, as you know, it's not easy to detect. So if you can detect, like large number of significantly statistically significant number of neutrinos, then it's possible. But that is at the moment that is the limitations.
So I mean,
But
neutrinos are not approved.
but the other way, what I can say, neutrinos are the neutral particles.
Yeah.
When we are talking about the solar storm, these are charged particles, and the charged particles are affected by the magnetic field and solar wind. Yes.
You are shown in 1859 event of the Carrington where that Colaba observatory measurements of, I think that definitely with the Earth's magnetism, where you have a sudden fall of almost 1600 nanotesla. Okay. Yeah. So, so that proves a very powerful this thing, that what kind of an event it has happened. What about in 2015 event? Did you check with this geomagnetism data, or do you have any parallel measurements of these things happening? I mean, you are doing in a cosmic rays, but what about directly Earth's magnetism measurements?
Yes. Yes, I have checked. There are several observatory. I told. Earlier it was Colaba observatory. So now they have shifted to Navi Mumbai, and they have observatory at Alibag, and they have observatory in Hyderabad and many other places. So I have checked the magnetic field data, but that is measured as so-called DHT index, and that time the change in the magnetic field is about 200 nanotesla.
Oh,
this event, our 22nd June 2015. Yes. 200 nanotesla.
8 times less than what?
Yes, yes.
Yeah. He just come.
Yes.
Let me see if there are. So, if any, Shashi want to ask question? Yes, Shashi, go ahead.
Yeah, I think it's not. It doesn't allow to unmute, right? Unless the host does that.
Yeah. Yes, Shashi. We had to do this due to some. Sorry for the inconvenience. Yeah, please.
Okay. So, nice talk, Mohanty. And I just wanted to ask about this L1 satellites. So they also would get such kind of signal. And so once you have a signal from the L1 satellite, then it comes to the Earth. So what is the typical propagation time for this magnetic storm between the L1 point and the Earth, if it is directed towards the Earth, of course?
Yeah. So it's about half an hour. Depending on the speed, for example, is 700 km per second, which took 36 minutes.
So L1 point is about 700 kilometers, is it?
5 million kilometer from Earth.
Sorry, you said 7. Oh, okay. The speed is 700 kilometers per second. Okay.
Yeah.
And for the change in the cosmic ray flux that we are seeing, that takes little 20 minutes higher than that. 28
minutes, yes.
Okay. And so in which case these L1 satellites can communicate, right, at the speed of light to whatever their control room is. Okay. If they have received the signal.
Yeah.
Okay. Thanks.
It takes 5 seconds.
Okay. Thanks, Mohanty.
Okay. Yeah, Rishabh.
Hello, sir. That was a really nice talk. My question is that have there been similar observations from other, let's say, Muon ground-based Muon observatories, and have there been similar delay times observed in those experiments too?
The question is, are there any other observatory around the world? They could measure this event. They observe this event. Yes. Yeah, yeah. So let me tell you the other that we checked the data. Several neutron monitors which are operating around the world, they could see some signature of the event. But however, you need, this is a change of about 1%. You need high sensitivity, and the GRACE 3 experiment it is sensitive. Its sensitivity is like several orders of magnitude compared to the neutron monitors. Okay, so in terms of, for example, if you combine the statistics of all the neutron monitors around the world, and the statistics of the GRACE 3 will be even larger.
Yeah. I think Rishabh's point is more towards like there is a similar set of neutron monitor that we're saying, that's a different kind of. I think what probably he's meaning, if you have other Muon telescope like GRACE 3, okay, and can they also be able to do similar measurements? So then that sensitivity part that you just said,
yes.
how would our sensitivity will compare vis-a-vis other similar setup? If you can say that.
Yes, definitely true. If you have other Muon telescope, ideally one need to have and a different part of the globe covering the entire globe. So that can, if you have similar area, you can have similar sensitivity. Yes.
No, I guess
that is the question.
Gagan's little bit. Maybe I didn't fully understand that, but maybe it will be nice since we also have a couple more minutes. Why the telescope at Ooty achieved such a phenomenal sensitivity vis-a-vis? I think that's what he's saying. Vis-a-vis other standard Muon telescopes, there must be a US.
Yeah. Okay. Yes. I will have to answer why the GRACE 3 Muon telescope is unique at the moment. First thing, it is the largest Muon telescope currently, so where he can get the very high statistics, so that it can measure a tiny variation in the change of cosmic ray flux. That is one part. The second part, it has a high directional and spatial measurements, because it can measure with angular accuracy of 4 degrees. So that is how it's very safe. For example, how we concluded this burst is local. This is due to transient event is local, because the GRACE 3 could measure this event in 9 directions simultaneously. Okay, so in order to have, you should have a good angular accuracy of the telescope, and you should have a high statistical measurement. These are the two.
Yeah, I guess there are no more questions. So since we are in person mode, it also gives an opportunity for us to also thank the speaker, going back by our old tradition of giving a small memento to the speaker. Thank you very much, Pravata.
Thank you.
Thank
you very much.
You enjoyed this beautiful.
Excellent. Thank you very much.
Okay. Thank you once again for a wonderful talk. Thanks.
Thank you.
I'm sorry. We actually didn't make arrangement. Thanks for reminding. So let us go for tea after the talk. Okay, so that maybe all people who are listening on the virtual media. So next time we can have more of them here. We are going for tea in the West Canteen. Please, all of you, please join. Yes, Pravata. Yeah, thanks, guys. Yeah. Thank you. Thank you.